one is RNN, recurrent neural network. So language model basically is a model that actually use a bunch of like the words as the input or a bunch of like sequences to predict the next word. Like the giving, the previous word, for example, which I think Yunfei is going to show us later to predict the next word. But it has some kind of advantage and disadvantages, which kind of motivates the utilization of the RNN, recurrent neural network, which I think Angelina is gonna cover later. So I will just like head over to Yunfei for the first part, which is language model. So let's get started. So Yunfei, you can share your screen right now.
All right, thank you, Daniel. Can anyone see the slide?
Yeah.
Great. All right, so my name is Yunfei. So today, me and Angelina will talk about the lecture 6, specifically the language model and recurrent neural network. So I will talk about the language model, and Angelina will introduce the RNN. All right, let's start. Okay, so what is language model? Language model is a very specific task of predicting what words come next by giving the previous several words. For example, let's look at this text. The students open there. So you guys can guess what should be the next word. What will be proper word for the next? Yeah. Oh, sorry. It could be books, right? Students can open their books. They can open their laptops. They can open their exams by to start the exam, and they can open their minds, which is abstract stuff. Okay, so what formally the language model definition is given by the below equation. So given the previous T words, we need to compute the probability distribution of the next word x t plus 1, where the tx1 can be any of the words in a fixed vocabulary list. And a system does this type of thing is called a language model. So it's a very specific task. Okay, we can also think of a language model as a system that assigns a probability to a whole piece of text. For example, let's look at a piece of text that contains T words. And the probability of this whole text, or you can see it's a document, by the conditioning probability definition, they can write into the px times px2 given the x1 words and go on. And the final results will be the product of actually a language model that we introduced previously. So yeah, the term inside is just the language model we just talked. So why the language model important, or like how do we use language model? So actually we use language model every day. For example, if we use our cell phone, when we type in I will meet you at, our cell phone will pump up with a few options like a cafe, airport, or office. They can populated by the pre-trained corpus, or it can learn your own behavior, that you type some patterns and then you later on the program remember, and then can give you something to relate most to your typing behavior. And another thing is we're using every day with the Google search. So we type in several words and we type in another letter, and or even without another letter, the Google will give you a few options that most relevant to your previous words. They can also be from the cloud, like the corpus can come from the cloud, or they can learn from your browsing history before. And also why the language model important. It seems like language model is a very specific NLP task, but actually it can be applied to many other areas as well. So a language model first is a benchmark task that can help us to measure the performance or progress of the NLP. For example, the language model, by giving the previous words, the language model have to understand the logic, the words, the logic, the structure for the sequence of the words, the syntactic meaning, and also the actual meaning in the words as well. So it can be seen as an overall benchmark for us to understand the progress of the NLP or understanding the language right now. And actually, language model is a subcomponent of many important NLP tasks, especially those tasks involving generating text or estimating the probability of a whole text. For example, the predictive typing is the ones we showed before. And speech recognition is a conditioning language model. So conditioned on the voice and or like the input voice, and they can generating a bunch of the text that better represent the voice. And another thing is the authorship identification. So the example is you train your language model specific to several authors, and then you use another piece of text, and then to put into your language model and to generate the probability of the text, and then the highest probability refers to the author that could possibly write this whole piece of text. Machine translation is a very hot topic, and the language model can be used in terms of generating the text as well, same as the summarization. A dialogue is an example of like a chat box. Chatbot can use the language model to generating the conversation as well. All right, so now we understand what language model is, and now the next is how do we learn a language model. So in the pre-deep learning times, we will see learn a language model by learn a n-gram language model. And by understand this, we have to introduce n-gram. So n-gram is a chunk of consecutive n words. For example, for the unigram, it's just a separate words. And the bigram is a consecutive 2 words. And trigram and the fourgram is similar to that. So the core idea about learn the n-gram language model is to collect the stats about the frequency of the n-grams and use this to predict the next word. Okay, so by learning the n-gram language model, we have to make a very simplified assumption. So the next word, t plus 1, will only depend on the preceding n-1 words. So here we're talking about n-gram language model. Actually, we're using the previous n-1 words to predict the next words. In total, it's the n-gram. It's a very simplified condition because, for example, we can have preceding like 100 words, but now we only want to build a 4-gram language model. We're gonna only use the previous 3 words. It's a very simplified estimation. And how do we compute this? So based on the conditional probability equation, we first to compute the t plus 1 words that appeared before, and this probability as a numerator, and the denominator is computed by the previous n-gram probability, and this division is the probability of the next word by the n-gram. And how do we get this n-gram and the n-1 gram probabilities? The answer is actually counting the frequency that it appears in the corpus. Basically, that will be our training data set. Okay, let's look at the example. So we're gonna learn a 4-gram language model. That means we will ignore the previous words until the previous 3 words of the next word. So now we only consider student open there and to predict the words after next. And the equation will be counting the frequency of the students open their next words, the counting of that pattern, and also divided by the students open their appeared in the corpus. For example, let's say the students open their in the corpus, it's appeared 1,000 times, and the student opened their books occurred 400 times. So the books appeared after students opened there will be 40%, which is 400 divided by 1,000. Another example is students open their exams. If it is occurred in the campus for 100 times, then exam to be appeared in the next will be 10%. Here is a question. Should we have discarded the proctor context, which means should we discarded all the previous words? Obviously, we shouldn't, because if we understand correctly, the proctor is related to the exam much more than the books. So if we ignore those, it's very likely that we're going to use the higher probability from the 40%. But if we consider the previous context, then we're probably going to use 10%, which is the exams. But if we consider the previous words, there will be not the 4 gram. Actually, it will be more grams. So there's a lot of a problem with this n-gram language model. The first one is a sparsity problem. For example, let's see the numerator. So the numerator, what if the students open their, for example, book, never occur in our training data set? Then these words appear, the probability will be 0. And this is going to give us 0 probability. By solving this, we can add a small delta to the count. So even it's never existing in our training set, we still can have a very small number, not 0. This technique is called smoothing. And a second sparsity problem is, let's look at the denominator. For example, the student open there is never actually appeared in the training set. That means this count will be 0. So from this equation, we can even compute this probability. By solving this, we can just use a technique called backoff. By actually considering the 4 gram, we actually maybe consider about 3 gram, trigram, or bigram. By backing off, we are likely to having more counts for the combination other than a student open there. We probably gonna use open there. So that's some trade-off or some methods to compensate this problem. And by increasing the n in the n-gram language model, the sparsity problem can be even worse, because the combination can cause the probability of the count to be more likely to be 0. And typically, to avoid the sparsity problem, we choose n not bigger than 5. Another problem with the storage. Remember that we use the backoff, right? So if you use backoff, we not only store the n gram, for example, 4 gram, we probably have to store n-1 gram into our model to compensate that sparsity problem. So that means so basically the model is just the key value pairs we stored. And if we have more n, higher n value, that means the combination the combination could be more, and then the total size of this you can see this dictionary or its model will be increased dramatically. So that's can cause the storage problem. Okay, so what's actually in practice is we look at the data set. For example, it's Luther's data set in the assignment 1. If we only train a trigram language model on our own laptop, it's only take a few seconds, which is pretty quick. And the result is basically we use that today, for example, to predict the next word. It could be company, bank, price, whatever. So that will be the distribution list that's generated by this language model. And you can see the first two are the sparsity problem. They're equal, so they're not too much granularity in the distribution. And the use case for the language model is generating text, one of the most important use case. For example, we used today this trigram language model to predict the next one, and we have the distribution list. We can choose sampling from the distribution list with the few highest highest probability. Here we choose the price. And next, we're going to use the price and to predict the next one. Here we're sampling off. And next, we're going to sampling on gold, and so on. So now we have a whole piece of text that generated by the language model, but also it's a human intervention because we're sampling from the distribution list as well. So after this, it's surprisingly grammatical coherent, but actually, if you read through it, it's not making too much sense. It's incoherent. So if we want to make our language model to be more coherent when generating the text, we probably have to increase the n value. And this increasing this can worsen the first sparsity problem, and also remember the storage problem as well. So given this, all these problems that are risen from the n-gram language model, now we have to think about some other language model probably can solve this those issues. So now we're entering into the neural architecture. So we'll think about to build a neural architecture to achieve this. So recall from the previous task, for a basic language model task, we just use previous t words to predict the t+1 words. And remember that we had the window-based neural model before in the previous lecture. The example was we used the 5 words: museums in Paris are amazing, and we use them as an input and input this neural network, and then to identify, oh, actually the Paris is a location, it's a name entity recognition task. So this neural language model is very similar to the ones that we've seen before. So let's look at this example. The students opened there. So we used a fixed window for example, 4 words, fixed window. And then we ignore the previous one. And we look up into the word embedding matrix and to find their corresponding word embedding. And then we concatenate into a column vector. So that's considered as kind of input into the next weight matrix. So this weight matrix giving you the hidden layer. So it's basically a linear layer with a nonlinear activation function. And the output for this, the hidden layer, will be put into another linear layer. And we apply a softmax after this linear layer, which giving you a distribution across all the vocabulary. For example, here we can see the books and the laptops are having the higher probability than the other words. So this model can solve the problem previously very well. So first, there's no sparsity problem because in each word, for each word in the vocabulary, you can always find an embedding, and you can always have this input, the word embedding input into this neural network. So there will be no zero output. And you don't need to worry about storing all the n-grams key value pairs, because all we need to do is to store the weight matrix W, the matrix U, and also probably your own word matrix for the lookup word matrix. So that's all you have to store. So it looks pretty excellent, but actually they still have existing problem because we still are restricted in a fixed window, right? So as long as you have a fixed window, you have a limitation to learn from the previous context. And actually there's the window can never be large enough, right? Because you have to, for example, the previous one, if you want to have the exam to be appeared next, you probably have to consider a few words more. So by enlarging the window size, this weight matrix will enlarge as well. So this can cause the training issues as well. And another issue is a kind of minimum, but it's also an issue. So for example, the input of the hot vector one hot vector x1 and x2. And when they input and concatenate into the weight matrix, they are actually dealing by a different parameters in the weight matrix. And this is causing us some inefficiency by processing the words. For example, when we're processing the words students, we should, the weights should share some information with the previous processing of the but actually in the word matrix, the parameter processing the and students are completely separate. So this caused some inefficiency when processing the words. So overall, the biggest problem is the fixed window problem. So now we need a neural architecture that actually can process any length input, which will give us even better result for the language model. So that's my part. If you guys have any question, you can ask. And then I will hand over to Angelina to introduce the RNN.
All right, question time. Any question from you guys?
I think it's very straightforward. Maybe no one.
I actually have a question or comment.
Okay.
Probably you can go back to the sample, like when you finish like a neural network, non-neural network, like the previous like a language model where you sample like the words in the final stage.
Oh, sorry, which one are you talking about?
Page 14, 13, I guess. Yeah, if you look at page 13, yeah.
Page 13?
Yeah, if you look at this one here, we don't actually select the word with the highest likelihood or probability here. So like I just want to say, this is a probability distribution. So we just randomly draw the word out of the distribution. It doesn't have to be the highest, the words with the highest probability. It could be other words over there.
Exactly. So if you are actually are dealing with this generating text task, you just need some like human intervention, basically just use sampling from the distribution.
Yeah, because in that way, we can take care of the problem of like we cut too much like context away. So in this way, we still can get access to some kind of like less frequent words, which probably gonna correspond to the previous example, like a proctor, like that kind of like the example you mentioned. Although the books has a higher probability, but we probably won't select that. We will actually select the exams because it's random draw. So I guess this kind of like medicate like some kind of like a static problem a little bit, but not like a.
Yeah, so it's not automatically. That means like you need the human intervention inside. Unless you want to automatic, then you have to put the exam to be very high probability.
Yeah.
In that example.
Sure. Yeah. Just want to comment on this. Yeah. Any other question from you guys?
Okay, seems no question. I will hand over to Angelina, and then she will introduce the RNN.
Okay, thanks, Yunfei. I'm going to, can you guys see my screen?
Yes.
Okay, so I'm going to introduce you guys the RNN. As Yunfei mentioned, in the fixed window neural model, here comes an assumption that there was a fixed window. So, however, in practice, we prefer kind of architecture that can process any learned input. That's why we need a new deep learning architecture, the recurrent neural networks. So basically, for most algorithms, there's one-to-one mapping between input and output. That is to say that if we have one input, we'll get one final output. And the inputs are independent from each other. But in some scenarios, like for example, we need to predict the next word from a sentence, it's not appropriate to take any of the preceding single word. We need not only know all the preceding words, but also the order between the words. If we treat every single word as a single input, we need the final output to be a predicted word from all of the preceding words. So these inputs are sequence data. They're related to each other. And also we need to include as many as input as we want. So for scenarios like this, RNN might be a promising solution. So this is a simple diagram that shows you the most significant features in an RNN. We have a sequence of input from S1, S2, F3, etc. And you can have as many as input as we want. Then we have a sequence of hidden states. Instead of just having one hidden state in the previous models, now we can have as many of them as we have inputs. So each hidden state, HT, is computed based on not only the input on the current stage, but also the previous hidden state, HT minus 1. So as it's stated in the equation. So the core idea here is we apply the same weight repeatedly in every hidden state. You can think it as a state that updating over time. It's kind of several versions of the same thing, which makes us able to process any length of inputs. Since we have the same transformations and weights in every step, so the weights won't change along with the length of the inputs. You can also have some outputs in RNN. These y-hats, these outputs are optional. So you don't need to always compute them. It depends on how you're going to use RNN. Here's a GIF that shows you how a single RNN looks like. If you treat the red port like an input, and blue is the hidden layer, and black as an output, as it shows, we have the same weights and transformations in each hidden state. And the results of the last layer will be taken into the next layer together with a new input. So I'll stop here. Any questions so far? Okay, I'll go next. So, okay, then let's take a look at how to apply RNN in language modeling now. Again, we take one sentence as an example. The students open there. So you can have a longer input, but I will just take a simple example first. So firstly, we're going to represent these words by one hot vector and use those to look up the word embeddings from our embedding matrix. This embedding matrix can be a fixed dictionary that you download online, or you download them online and then fine-tuning the parameters by yourself, or even something that you train from scratch. So then to compute the first hidden state H1, you need to know the previous state H0 and the current input E1. The initial hidden state H0 can be something from your experience that all you learn, or you just assume them as zero vectors first. Then the formula to calculate the next hidden state is as presented on the left. It's kind of, first of all, it's kind of a linear transformation of the previous hidden state and the current input. And you can also add some bias. And then we do some nonlinear transformations, activation functions, like for example, sigmoid or tangent. And then you keep on doing like this, you will get the rest of the hidden states. So here we need to do language modeling. So we need to predict the word after the students open their blank, right? So on the fourth step here, we can see that this hidden state H4, we can put the H4 through a linear transformation and a softmax function. Then we can get a distribution y hat 4, which is a distribution over the whole vocabulary. Then we can get some estimates on what the next word should be. So here we can take a look at a more visualized example. The question here is, what time is it? So hopefully by applying RNN, we can get a reasonable answer to this question. As it shows in the diagram, the second hidden state contains information from the first hidden state. And the third one has information from the first and the second hidden state. And accumulatively, the fifth hidden state have information combined from the previous 4 hidden states. And the output 05 will be the answer to this question. So here is just a basic idea of how the RNN language model is working. A very obvious advantage of RNN is it can process any learned input, and computation of each step t can use information from many steps back. The other advantage is the model size doesn't increase for longer input. The size of the model is fixed because we apply same weight in each hidden states. It's just WH and WE, and some bias maybe. So no matter how long your inputs are, those model parameters won't change. The next advantage is RNN is more efficient method comparing to the traditional neural models. So unlike the traditional neural models, it applies the different weights to different inputs. We apply same weights on different inputs on each time step. That's to say that the transformation of each hidden state is the same. So once it learns a very reasonable weight, it will apply to the rest of the inputs. So it will be more efficient. There are also some disadvantages of this model. So first of all, the recurrent computation is quite slow. As I mentioned, each hidden state is computed based on the previous hidden state. So that's to say the hidden states cannot be processed at the same time, especially when the inputs are pretty low. The other disadvantage of RNN is it is very difficult to access information many steps back in practice. And in addition, as you can see from the GIF, so here, the short-term memory has a greater impact on the final output, such as the orange areas and the red areas. But long-term memory has smaller impact, like for example, the black and green areas. So this is a very typical short-term memory issue of RNN. So, but disadvantages can be overcome by more advanced RNN models afterwards, like the LSTM and the GRU. Maybe you could probably learn by yourself afterwards. Any questions? Okay. Okay, then I'll go next to learn how to train an RNN language model. So as a start, we will get a big corpus of text, which is the sentence of the word, X1, X2 to X capital T. Then we feed this sentence of words into RNN language model. We compute the output distribution Y hat for every step. This means you are predicting the probability distribution for every word. So once we've done that, we can calculate the loss function. It should be a cross entropy between the predicted probability distribution Y hat T and the true next word YT. As we know before, the cross entropy can be written as a negative log probability, right? So for example, these are all the loss for each given words. And then after you get the cross entropy loss at every step, you can sum them up. Then you average the sum, you can get the overall loss of the entire training set. So here's some notes when you train the RNN language model. The computing loss and gradients along the entire corpus could be very expensive, especially when you get a very large and long corpus. So in practice, we usually consider X1 to XT as a sentence or a batch of sentences. So like some smaller unit of text. That's to say, we usually compute loss on a batch of sentences and compute the gradients with respect to the batch of sentences and update the weights and then repeat on every batch. So before I move on, do you guys have Any questions? Okay, then we can move on to the backprop. So I don't think I will go too much details here because we've learned the backprop in previous lectures. I just need to mention one point here. So there's a very like characteristic thing about RNN is we apply the same weight repeatedly, right? So the question is, what is the derivative of loss function with respect to the repeated weight matrix WH in every step? So as the equation presented, the answer is the gradient with respect to a repeated weight is the sum of the gradient respect to each time it appears. So the notation with the vertical line and I says that the derivative of loss respect to the WH when it appears on I step. Then why is it like this? So if we apply what we've learned in calculus, the multivariable chain rule, we can see that the derivative of loss function with respect to the repeated weight matrix WH at each step t can be written like in this formula. As we go back to the equation of how each hidden state is calculated, we can see that the HT, for each hidden state is computed based on HT minus 1, and HT minus 1 also depends on WH. So we cannot use this single formula anymore. In this scenario, as you can see in the left bottom diagram, WH has a relationship with all this individual appearance of WH. So if we apply the multivariable variable chain rule here, we can get this equation. So the derivative of loss function with respect to WH is the sum of these chain rule things. But the expression on the right is just 1 because we keep using the same weight in each step. Then by remove that part equals to 1, it gives us the final equation as shown in the previous slide. So do you have any questions about the backprop so far? No questions? Okay. Then we can talk about how to evaluate the RNN language model. So basically, we need some measurable metric to evaluate the performance of deep learning models. So the standard evaluation metric for language model is perplexity, which is the inverse probability of corpus. So if you look at the formula, it is saying that for each word xt, we compute the probability of that word, given everything that came so far, and get inverse over that. And then we normalize the product by the number of words, which is capital T. So the reason why we do normalization here is because if you don't do normalization, your perplexity will get larger and larger as your corpus get bigger. So after some transformation, you can also see that the perplexity is equal to the exponential of the cross entropy loss, J theta as well, which is to say that if we train the language model to minimize the cross entropy loss, then you train it to optimize the perplexity as well. So namely, the lower perplexity is, the better the model is. Yeah, I think that's all for my part. So before I hand it over to Daniel, so do you guys have any questions regarding RNN models? No? Okay, then I'll hand it over to Daniel.
Okay, so now it's more like a discussion time. Do you guys have any question regarding the language model and RNN right here?
So not a question, just a comment.
Yeah.
The perplexity part is pretty important. That's what I got for my recent interview question. Like how do you evaluate a language model? I think I forgot about that during the interview. So
Okay.
I said I don't know. So just want to point out it's pretty important.
Yeah, the perplexity can be used for any evaluations in language models. Like you can also use it for the fixed window neural model as well. And also some more advanced RNN or advanced NLP models. So it's a very standard evaluation matrix.
Oh, I have a comment over here as well. So you can even use perplexity in multi-class classification problem as well.
Yeah.
So it makes sense.
Yeah, perplexity on Earth is actually originally designed to evaluate the probability distribution prediction. So it's for the probability. So as long as you have the model that actually involves in the prediction on the possibility or probability over something, just like a language model, pretty much you can use a perplexity over there. Yeah.
Yeah. Thanks for the comments.
Just one question here, for all of you guys, did you guys get how to do the back propagation over time for the RNN over there?
Maybe you can show them. You can show them that how you compute the backprop from scratch.
Yeah, because I actually had several interviews asking me that kind of question too. So I guess maybe I can show a little bit because sometimes they usually ask me to derive the equations myself. Yeah, so I would just
on the interview.
Yeah. So sometimes just ask for backpropagation. What is a backpropagation? So the first question usually likes that. Second, oh, I gave you this kind of activation function. Can you do a backpropagation for me? So on the whiteboard, then it was you have to do all this kind of from beginning to the end, especially for the machine learning, engineer, kind of the roles up there. They will all ask a lot of questions about backpropagation, almost every single time, actually.
That's interesting. Maybe I can ask for some interviews next time.
Yeah, right? I mean,
I've never asked questions like this in the interview.
You don't have to be that specific, but you need to know what backpropagation is, right?
Yeah.
So that's the basic foundation for a neural network, I guess.
Yeah.
So I'm gonna actually broadcast. So yeah. So basically what Angelina just said is totally correct. So she just give you a high level kind of summary of what backpropagation here. But it's actually not that complicated. So it's a little bit different than the previous backpropagation. So for example, suppose we have the four, 1, 2, 3, 4, 5, maybe it's 5. If you don't count the input a hidden layer is a 4 layer here. Suppose we have the 4, kind of hidden layer RNN right here. And what we try to do is, I try to calculate, because this L4 here, a G4 here, this is a final stage. So basically that's where you get the output, pre-stage before you get output. So what we do here is we do backpropagation in that direction, right? We use that. Suppose we try to figure out what kind of optimal parameter we have for the WH, for example, for that one. Suppose we focus on that one. We try to actually do the backpropagation on WH. Then we should start from here because that's the last step according to the definition of backpropagation. So basically the question is, what is that? What is the first order derivative of G4 with respect to WH? Or here, I just write a W here, okay? So if you, we can start from the immediate, hidden layer right here, right? So G4 depends on Y4. And a Y4 depends on H4, right? So here and here, right? So the first kind of step is you have to do the first order derivative of this, G4 with respect to Y4, then Y4 with respect to H4. Then you do H4 with respect to W here. But just like Angelina just said, H4 is actually a function of WH and H3, right? Because H4 equals 2. Suppose we have the sigmoid, kind of like an activation function that is WH3 plus WX X4 plus B, right? So basically, that's what H4 is. So that means H4 has two components. One is W here, which is related to WH, and another one is H3. So we have to decompose a little bit. So at the end, after that, next step would be, first of all, I have this kind of like a derivative. Second, I have H3 over W here. Okay, so because H4 not only depends on W, but also depends on H3. So that's why I just, can decompose a little bit. But wait a second, this is not the end of the story, because H3, just like H4, just like how we decompose H4, we also have H3, which depends on H2 and W as well. So W is everywhere. It's in every hidden layer. So we do that again. We already have the first one. Now we decompose that one. So we have H3 with respect to W, then H3 with respect to H2, and then H2 with respect to W here. Okay, so now that's where the chain rule just kind of like, comes in here, because you have the nested, kind of like a structure for all the ways here. So we keep doing that for H2 until we get the end. We got H2 over, with respect to W here, and H2 with respect to H1, then H1 with respect to W here. Okay, so that's basically the end. So that's the last step. So basically you have this summation here. Okay, a bunch of like summation here, right here. So in summary, like formula should like this. Okay, and nothing changed for the first two components, like ET with respect to YT and YT with respect to HT here. Nothing changed here. Okay, because when we do the G4 with respect to Y4, it's everywhere. So this part doesn't change, because it's only G4 and Y4. What changes is, the last part, last component here. Okay, that's the last part which changes. So H3, H4 over W, H3 over W, H2 over W, so on and so forth. So basically, that's how we do the backpropagation through time. This is a little bit harder than the I would say like the normal RNN, like artificial neural network backpropagation, because it has like some actual part here, which is kind of like I actually, it took me some time to understand this part myself. So yeah, that's how we do the backpropagation through time. Any question for this part?
Sorry, what's the difference between the top part and the bottom part?
Which part? Which part did you say?
The top part and the bottom part. What is the, okay, so G4 theta.
Yeah. So G4, Y4,
W.
Y4, H4, H4W.
No, I mean like the top and the bottom, they are different, right? Like these backpropagations, are they the same thing or they're different?
This part, like these are the same. Those are always the same. First two components are always the same. It's just the last component which are kind of different.
No, I mean, can you zoom out a little bit? Yeah, I mean the blue part and the red part.
Okay, so if you want to do, okay, let's start from the beginning. If you do like a first order derivative of G4 with respect to W here, you have to do G4 over Y4, because W is in Y4, right?
Yeah, I understand the blue part, the red part down below.
Okay, so what is, so the question here, let me write down here. So that's, yeah, that's like the part which is kind of confusing. H4 equals to WH3 plus WX X4 plus beta plus B, right? So as you can see here, H4 depends on W show up right here, right? But inside here, there's also a WH, right? So we have to do the first order derivative twice on two like separate components. One is on W here. One is on H3, then H3 over W.
Yeah, no. So I understand all the blue part. Just like from the red font, this can be written as. Is
This
this
part?
like continuing the previous part, or this is something new?
Oh, this part right here?
No,
No, down
the
there.
formulas you written in
Oh,
red.
this part. Oh, that part. Oh, okay. The red. Okay, sorry, I misunderstand the question here. So this is actually the example of showing this formula here.
What
So
is that?
basically, yeah, that's how I actually just use the G4 as an example to show this kind of like a green kind of dash like a formula here. So the first kind of like a part you have to do is always H4 over W. Then you do H3 over W. Then H2 over W, H1 over W here. Okay, and before that you do H4 over 4, H4 over 3, H4 over 2, H4 over 1. And this part need to be decomposed a little bit more, which actually correspond to what I did here. But the formula didn't actually show you how to actually expand that part. But I remember, yeah. So basically here you have to expand the part yourself. So it's not that easy. So my suggestion is like that I really, the reason I don't want to get into that part is like this is kind of confusing. This is really kind of confusing, especially when you look at that part. So basically you don't do H4 over H2 directly. You have to do H4 over H3, then H3 over H2. So I think a better way is actually to do this yourself and try to figure out how this kind of chain rule works from one layer to another. But the formula is totally right. It's just like you need to do a little bit more work like this part for yourself. Does that make sense?
Yeah. So that confusing part, is that computing the same backpropagation, or is like yeah, I'm still confused, I guess. So
it's actually so this part and
yeah,
that part the same.
they're the same. Okay.
Okay, yeah. So yeah, see, so
So
if you actually look at that part, it's not confusing. But if you go to that part, it's kind of confusing here.
Right. Okay. Yeah. Okay. Cool.
So I don't actually suggest, like the formula is totally right. There's no way that this formula could be wrong, but it's just like, this is the abstract. Think about this is the abstract version of what I just did here. So in an abstract way, for example, if you look at this part, H4 over H2, we don't do this directly. So what do we do?
Right.
H4 over H2 is H4 over H3, H3 over H2, then H2 over W. So basically, it concatenates everything in one single term here. But it doesn't mean, we just do the direct derivative of H4 over H2. So inside this, there's another component H3.
Mm-hmm. Okay, cool. Nice.
Yeah.
Understand now. I have another question. So during the backpropagation, we only compute the loss once, right? Like we only compute after, like, say, all the interim steps loss is calculated, and then we accumulate them together and then do the backpropagation only once, and then use that loss to update the parameters.
Yes. Basically, that's how we do. But sometimes, like you probably know, Levin, we have many mini batches out there. So for each mini batch, we are going to do this, once. So it depends on how many mini batches over there. But theoretically, it's once. Yes.
Okay. Cool. Thanks.
Yeah. So yeah, my suggestion is like, do not really go to that part. Do not really go to the notes part, because when I the first time I actually just go to this part, it's super confusing. It took me like a half an hour or 1 hour to actually figure out how this whole bunch of stuff is calculated. So you better just like follow this kind of like calculation yourself, which I will upload later, like this page to the.
What is that diagonal thing? The W, like the yellow part, WT times diagonal.
Oh, this part is what I told you. Like when you do H4 over H2, it's actually a multiplication of H4 over H3, then H3 over H2. See, this is multiplication here.
Yeah, so go even further. So
this one?
WT, is that like a diagonal of that matrix, or what is it?
What is H3, what is, for example, if you do H4 over H2. So if you do H4 over H2, right, equal to H4 over H3, then H3 over H2. then what is this? That is actually W, right? So you basically just factor out W here. Because every single time when you do H4 over H3, it gives you W. But it's in here too, so you give another W here. So that's really hard to explain. So let me just write.
So you can write a function that how to calculate each hidden state. That because for each hidden state, it will like I can write a function.
You get what I mean, right? So basically, you have a W every.
Yeah, you have a W. You have a W in front of like.
Yeah,
you have.
So you can figure out that coefficient for every single previous age. So that's why you have a W here.
And the DIAG means?
DIAG is actually the next part. So for example, H4 over H2, H4 over H3, H3 over H2, right? What is this part? That's,
no, that's W.
That's W. Yeah. So this is actually that. Because it's not over yet. So you can still actually do, so yeah, that's actually over here. So basically that's the, differential here.
Yeah, I'm just, yeah. So DIAG, is that diagonal? I don't know.
It's diagonal, yes, it's diagonal. Because H4 is only, because it's only kind of like, along the diagonal. It doesn't actually go somewhere else. Like if you look at this, this is another one, but yeah, it's diagonal. It actually doesn't come to other, because H4 only corresponds to H3, then H3 goes to H2. You don't actually jump from H4 to H2 directly.
Okay, yeah, interesting. Yeah, I guess it's pretty complicated.
Yeah.
Yeah, I just don't understand why it uses diagonal. I saw it in the video, but I just let it pass. So. Yeah.
So I would say, like, let's think about it this way. H, what's the dimension? What's the dimension of H? Or what's the dimension of WH here?
WH is the size of the WH depends on the
input, right?
No, it depends. The number of the number of layers depends on the input.
Yes.
The number of WH depends on the size of the input.
Yes, yes. So basically, yeah. So you can think about, right. So WH actually depends on that one, and WH depends on one. So for example, suppose the hidden size is n. If hidden size is n, then WH should be n by n. Does that make sense to you guys?
M should be, because like WH needs to, okay, so WH, WE.
Yeah, so basically, I think I have the notes on this part. Yeah, so WH is n by n. For example, if the hidden size is n here, WH should be n by n, because this is 1 by n, then you time n by n. Basically, you have another 1 by n here. Does that make sense?
What about WE? When does WE come in?
D by
so,
n.
The WE is something that you download. Like this is embedding matrix weight, right?
Yeah,
so
sense.
You can train from scratch or from like you download online that has some dimensions already. So it depends on how you initialize the WE.
Exactly. So the dimension, like the dimension for the embedding is up to you. You can denote that as a D. So if that's a D here, so WE should be D by n, because here is 1 by D matrix and times D by n. At the end, you're going to have 1 by n matrix. So that matches with the H size.
Yeah, that makes sense.
Right? So if Wn is n by n matrix, then when you do the H, for example, H4 over Wn, I'm actually going to derive this myself. So this should be n by n matrix as well, right? The derivative. Does that make sense? Because every hidden size, you have to do every component here with respect to W here. And W is n by n matrix. So basically, think about this way. each H is 1 by n matrix. I'm gonna write down here. Each H is 1 by n vector. You can think about that way. And WH is n by n, right? So when you do the first order derivative of this, it's gonna give you n by n matrix. N by n matrix here. But the dimension here is only one, like, 1 by n. So basically, 1, 2, 3, 4 until n. You make this derivative with respect to a bunch of, 1, 1, W1, 2, W1, 3, like a bunch of, like, all the H here, right? Yeah. So when you do that, it's gonna give you, so basically what the lecture just said, it's gonna give you a diagonal matrix. Why is diagonal? Because you don't have like n by n matrix here, so that you can do the, the 1-to-1 derivative. You actually have to do this 1, 2, 3, 4. So it's along the diagonal. It's actually everywhere. So intuitively, that's how I'm thinking. But a specific duration I haven't figured out. But this is like intuitively how it's not everywhere like n by n matrix. It's actually still n by n matrix, but it's not. It's like nothing else except for the diagonal here, especially this part. Okay.
I see.
Does that make sense a little bit? I haven't derived myself, but that's how I'm thinking. How this works. Maybe we can go a little bit more into this, but I actually haven't go that deep here.
I just saw it in the slides, but I didn't understand like when I watched that. So
yeah, I probably we need to go back and and think about this a little bit more. But fortunately, I haven't been asked that question in the interview yet. So yeah.
Okay, cool.
Yeah.
Thanks.
Any other questions? Yeah, okay. I just want to make one comment on the RNN. Like, just Angelina just said, like previously, how last layer is going to keep all the information from the previous layer. But one kind of question I always ask myself, like, why RNN? How does this RNN correspond back to the language model we had previously, like this one here? Like, how does this correspond to, the language model we had before? What's the connection between this and that? So I looked through some kind of video there, and it turns out it's very kind of straightforward. For example, y1 here, or h1, depends on x1. When you move to the next time step, so each one here is called a time step. When you move to the second time step, y2, it depends not only on x1, but also on x2. So previously, in the first time step, we have this. Y1 depends on x1. When we move to the next step, then y2 depends on x1 and x2, right? So what is this? This is actually the language model itself, but it's unigram, bigram. So we can do this again and again. So for this one here is x1, x2, and x3, trigram. So until the end, what do? We actually collect all the previous grams and use that to predict the YT. So that's why, how we are going to use RNN, because RNN, is actually take over all the previous information, one layer after one layer. So it's kind of accumulated here. At the end, this is actually the language model, which is very, which is kind of surprising. So that's how the language model is constructed, which corresponds to the same kind of architecture or construction of the neural network. Okay, so if your problem is just like this, you try to use all the previous information to predict for the next kind of part of whatever you want to predict, then RNN is probably the best kind of choice for this kind of structure. So not only for language model, but for other kind of models similar to language model, which is correspond to using the previous information to predict the new kind of information you want to capture then RNN is definitely like one of the options you should definitely consider. Okay. Yeah, so basically that's what I want to highlight for RNN and everything here. Any other questions? No? No other questions? Okay, if you guys don't have any questions, like we can call it a day. So I was thinking about actually giving you guys some kind of like a guidance or some kind of my kind of personal solution of assignment 2 today. But I guess maybe we can merge that with assignment 3 together because you know, I didn't actually prepare that today. I thought this kind of lecture could take like up to 2 hours. So I guess we'll have open another kind of lecture independently, combining assignment 2 and assignment 3 together and go over all solutions together. And I hope that actually makes sense to you guys. And I apologize for, you know, not actually prepared for that today. Yeah, that's basically everything. If you guys have any question, feel free to post up in the chat group, WeChat group. And Angelina and also Yunfei's already uploaded the slides to the Google Drive, shared to everyone. So yeah, really nice discussion with all of you today. And I hope you guys have a nice, like, you know, Sunday, and talk to you guys next week. And thank you so much. Thank you to Angelina and Yunfei. Thank you so much for your work.